Okay, good. So I think I now need to click on, is that going to change now? No, it's not. I need to click on the slide. Great. Okay. So this is the functional that we've sort of seen so far. So this is maybe a slightly different mathematical form, but this is a Koopmans functional, right? So we've got a Koopmans functional is a corrective functional to density functional theory. So we start off with some base functional. This is a rho dft. And then this here is our term that is imposing this condition of the fact that our eigenvalues should correspond to total energy differences, or this sort of piecewise linearity. But so here, this sum I here is over each orbital in our system. And so this is a sort of, we're applying this correction orbital by orbital on our system. And so this first term here is the term that removes this erroneous dependence of the orbital energy on its own occupancy. And here we're replacing it with a term that's linear. And so the effect of this is to sort of impose this piecewise linearity. But actually, it's more than piecewise linearity, right? Because we saw yesterday that the piecewise linearity condition is a statement about the change in the total energy as you change the total number of electrons. Whereas here, we're imposing this condition on the orbital by orbital. So this is what we call a generalized piecewise linearity condition. And it's a sufficient, but it's not a necessary condition in order to impose piecewise linearity. But as we've seen this morning, it's a very good idea in order to extract good orbital energies. Now, the key differences from this functional to a semi-local functional when it comes to actually performing these calculations are that we have these different flavors that we had mention of already. We have this orbital density dependence, and we've got screening that we need to account for. So I'm going to sort of talk about these now more in detail. So firstly, the different flavors of Koopmans functionals. Basically, in this construction that we've written down in this corrective term, there's this sort of this gradient that we're going to put in. So we're saying that our the orbital energies should be independent of their occupancies, but that doesn't say anything about what total energy they should correspond to. And so this is where the sort of freedom of choice comes in. And so here now I've rewritten this as explicitly the Ki functional. And so we replace that term at the end with specifically the energy difference between integer endpoints as calculated using the base functional. And so this was the version of the functional that does not affect your energy or your density. And so this is sort of I like to think of this as the core idea, but the core Koopmans correction, in the sense that this is the minimal correction that one applies that can impose this linearity condition. So with the KIPZ functional, which is next, is basically involves also an addition of the Purdue-Zimmer correction, and that starts to do stuff to do with self-interaction correction. But really the Ki functional is really this minimal correction that will enforce this piecewise linearity condition and does nothing more. And so sort of to add my 2 cents on to answer Tomas's question, I think really the nice thing about the Ki functional that we can take advantage of is that because we don't change the total energy, computationally it's very cheap, because once you sort of do a semi-local calculation and you obtain the density, then the Ki correction is basically a post-processing step. And so whereas the KIPZ functional, that changes the density, and so you need to do a much more extensive calculation. And so this sort of opens the door to doing some much larger calculations where in reality you probably couldn't afford to do an ODD calculation, but we're just doing it as a post-processing step. And finally, you might also see mentioned, I think, on the other slides, there's the PKIPZ correction. So this isn't just the KIPZ Hamiltonian, but you evaluate it on the Ki solution. So it's because KIPZ is a bit more expensive, you can just have this sort of halfway measure. And then also there are older versions, I think there's the K functional that we no longer use, but you might see that if you look at the older papers that are around. Okay, and so the second topic is this orbital density dependence. So here's this sort of correction that we're going to apply to each orbital. And then here is you can just rewrite it out explicitly as There's a combination of these hard to exchange correlation energies. And then if I take this energy term and derive the potential that gives rise to this energy, it's given by this expression here. And so here we can see that we've got, well, this is in the specific case of I've got an orbital that is filled and we're dealing with the Ki functional. And you can see here explicitly, we've got this dependence on orbital density. So here, Ni is the density of a specific orbital. And so this is what Andrea was mentioning, is that now we've got as many potentials as we have orbitals in our system, but each of these potentials is local. And so in practice, when we're performing these calculations, because we've now got this orbital density dependence, we now need to minimize the total energy with respect to the shape of every single orbital in your system, not just the density. And so if you're going to do this explicitly, what one often does is you initialize with a solid, you might initialize them with maximally localized linear functions. But then, like Nicola was saying in his answer to you, Gabrielle, when we perform this energy minimization, we obtain the variational orbitals. There's nothing arbitrary about this. They're well defined as a minimum of our total energy functional, because our energy is a functional, well, yeah, our energy depends on the shape of individual orbitals. And so when we perform these calculations, we do this with conjugate gradient minimization. And practically, we do this as sort of a inner and an outer loop step. So in the outer loop, you just perform a brute CG minimization. And then the inner loop, we perform these unitary rotations of individual orbitals, which in principle is not necessary, because these sorts of transformations between orbitals is possible within the outer CG minimization loop, but we find that this makes things more efficient. And so we'll probably see this in the hands-on later today, this sort of CG minimization of all the orbitals in our system. So, like we saw earlier, when you perform this explicit minimization of the total energy, this gives rise to this set of variational orbitals. And these are typically very localized. And then once you're at the minimum and then you diagonalize your Hamiltonian, this gives us the canonical orbitals. So we've got these two different sets of orbitals, and they're related simply by a unitary rotation. So, or in other words, a mixing of the two. But both sets give rise to the same total density. They're just equivalent. They're just equivalent representations of one another. Yes. So we saw this plot here earlier in Ismail's talk, but I thought I'd just really drill down on precisely exactly what's going on here in a bit more detail, in terms of to stress the importance of localization to the success of Koopmans functionals when we perform calculations on solids. So this plot here is showing the ionization potential. So this is the energy of the HOMO, well, the negative of the energy of the HOMO, so the amount of energy that's required to remove an electron from the outermost orbital. And this is for a set of different alkane chains of increasing length. So over here, we've got C2H4, and then all the way at the end, we've got an infinite chain. We've got polyethylene. And so here, first I want you to concentrate on the black and on the yellow curves. So the black curve is the result that you get with PBE if you just look at the HOMO energy. So we know because that this will not give us the right result, right? Much like the PB functional gives us the wrong band gaps. It's so there, if we look at the molecular limit, it's down here, whereas experimental result here is this blue point up here. Whereas the delta SCF result is much better, right? So so when you explicitly just remove an electron from your system and calculate total energy differences, the PBE gives us excellent results. And this is because really, I mean, density functional theory is a functional about total energies. And so the eigenvalues are sort of auxiliary quantities that usually we have no right at sort of inspecting and trying to extract sort of physical meaning from. Now, as we go towards the bulk limit, we can see that these two results converge to the same value. And now note that this value is different. So what's happened So these two results, now both of them are bad with respect to experiment. So what's happened here is that if we think about what happens when I add one electron in the bulk limit, so for one cell, it's going to have a total energy difference that's given by the energy of the electron where I've removed delta n electrons from that one cell relative to the neutral system. Now, if I think about across all the cells, my total energy change will be the number of cells, and so the number of cells that I have in my system is just going to be 1 divided by the fraction of electrons in each cell, times by this total energy in my cell. But then this here is nothing less than just the derivative of my total energy with respect to the total number of electrons. And so by definition, this is the HOMO energy as given by Gannick's theorem. So basically in this bulk limit, these two methods just have to agree by merit of the fact that in this bulk limit, they're mathematically equivalent. And so really the issue here is that we've got this sort of, firstly, we've got eigenvalues that fundamentally we shouldn't be looking at in order to extract meaningful excitation energies. But now furthermore, the delta SCF method, it breaks down in the sense that it no longer is going to give us no longer can accurately tell us the total energy difference when I remove a very delocalized state from my system. And so we have sort of two alternatives here. One would be to sort of start looking at different functionals that are better at predicting really what is the total energy difference when I remove a very diffuse state from a bulk system. Or the alternative, which is what we follow, is that we don't ever inspect the total energy differences when we remove an electron from a very diffuse state, but instead we always perform the calculations with respect to removing an electron from localized states. And so this is what happens along these curves up here. So what these correspond to are, I'm performing a Koopmans calculation, but when we construct our Koopmans functional, we always inspect the removal of electrons from maximally localized vanilla orbitals. So we don't remove them from the canonical orbitals, but we're looking at the process where I remove electrons from variational orbitals. And so by applying the Koopmans correction to the variational orbitals rather than the canonical orbitals, we get this nice and sort of bridging between the sort of the molecular limit, where we already perform very well, but also all the way to the bulk limit. And so basically what's happening here is that we're very accurately modeling the process of removing electrons from individual variational orbitals in our system. And then the resulting HOMO that we extract is sort of a built up of a linear combination of the process of removing electrons from individual variational orbitals in your system. And so this is this also means that it's very nice that our system gives rise to the set of localized orbitals that we can already naturally use in order to do this smooth transition between the molecular and the bulk. And yes, and the other side note is that in the limit of an infinitely diffuse orbital, also our Koopmans correction is also vanishing. So these various terms in the Koopmans correction would actually go to zero. So a Koopmans correction to a totally diffuse state would also be zero. So the fact that we can now operate on this very localized basis keeps us safe. There are a few other features of orbital density dependence that I would just like to briefly mention. Firstly, having an orbital density dependent functional means that we know the action of a Hamiltonian on a set of orbitals, but in general, we don't know what the Hamiltonian is. Practically, we often use maximally localized vanilla functions, so sometimes we don't bother with the actual process of minimizing the total energy functional. We just use these maximally localized vanilla functions, and Nicola will probably mention that more in his talk. And as we saw with Andrea, the sort of ODDs are a natural generalization of a DFT in the direction of spectral functional theory. And then finally, this last ingredient that we need to think about with these calculations is the screening that is present in these calculations. So we've got these alpha parameters. So sort of just to try and demystify screening a little bit, I thought I'd first talk about what we think about. So we'll first talk about Hartree-Fock. So the original Koopmans theorem, so where we take our name for our method, is actually a theory about Hartree-Fock. And it's basically a statement that the ionization potential, well, the Hartree-Fock energy is a linear function of the orbital occupancies. And so, I mean, you can see this because, well, this appears to be quadratic, but actually, if I is equal to j, then this term cancels with that term, and so the total energy vanishes. And so the end result is that the Hartree-Fock energy is linear with the orbital occupancies. But in this sort of argument, I've actually made a mistake, and this is that I've neglected the fact that the shapes of these orbitals will be dependent if I change the occupancy of an orbital. So if I change the occupancy of an orbital, these orbital shape will change, and actually it won't be strictly linear. So actually Koopmans' theorem applies if you neglect orbital relaxation. So it only applies in that case. And so actually it's because of orbital relaxation that when you look at Hartree-Fock, it's got this erroneous concave curvature with respect to the number of the total number of electrons when we are looking at those classic E versus N curves. So the idea behind Koopmans functionals is we do the same approximation when we derive the Koopmans functional, going from this sort of core idea of trying to impose this generalized piecewise linearity condition and deriving our functional form. So we neglect the dependence of our orbital densities on their own occupancies. And so because we do this, we need to account for it post hoc. And so the way that we do this is we pre-multiply, we scale our corrections with some screening parameter alpha. And so this is just some number between 0 and 1. And we've got one of these alpha parameters per orbital in our system. And so, and this accounts for this orbital relaxation or screening. Now, of course, this begs the question, how on earth do you work out what this alpha parameter is? It's all very well for me to sort of write it like this, but now all I've done is lump the sort of what I don't know how to calculate into this alpha term. And so the trick here is, what we do is that we choose a value of alpha by returning to this original idea behind Koopmans functionals, in that we want to have these orbital energies correspond exactly to total energy differences. And so if we imagine I've got some orbital in my system as a function of the orbital occupation, and so if in this case, I'm looking at what is a filled orbital in the neutral system, and then if I say remove the electron density from this variation orbital, the energy will increase to this value here. Right, and so in principle, I want this to be, I want it to be piecewise linear between these 2 points. And if I were to use just calculate this with my base PBE functional or LGA or whatever base functional I'm using, I'll get this erroneous curvature. And so what we do when we try and calculate these screening parameters is we inspect these quantities here. So this is the expectation value of the Koopmans Hamiltonian. I've written it here explicitly so we can see the dependence on alpha. And so this quantity is basically the gradient of the energy curve. So here, if I calculate this lambda II, but here with alpha set to 0, I'll just get this gradient here. So I can do a calculation of a DFT calculation of the N electron system, and I'll get this value here. But also I can do a calculation with just some guess value of alpha, and I'll get this. I'll then manage to extract a different gradient for this a different expectation value. And so just looking at this figure, it's sort of immediately obvious that basically as we assume that if this quantity here is in fact linear with alpha, then the correct value of alpha, the ideal value, is just going to be given by this formula here. So here we're just working out how much each of these deviate from the the desired gradient that we're after. And so this formula here gives us exactly the right value of alpha that we want, that will guarantee that this line here points in the right direction to satisfy this piecewise linearity condition. And so in principle, this is an iterative process, but in certain cases, like the Ki functional, where actually the total energy with the Ki functional is simpler, actually, this is guaranteed to converge within a single step. So just to drill down on exactly the ingredients that we need to calculate for these in order to obtain these screening parameters. So here, this is the expectation value of our Koopmans Hamiltonian calculated on a variational orbital, and this is the same for DFT, for the DFT Hamiltonian. So these are very easy to extract from an electron calculation. That's the total energy of our neutral system, but then this guy is the difficult one to calculate. So this is the total energy of our system when we've removed one electron from an orbital I. So basically here we're just wanting to calculate the energy of a charge defect. It was the one on the left, right? Okay. Left. Yes. Okay, so this is the one that is difficult because in principle for a solid, you need to make sure you avoid the sort of spurious interactions between charge defects, and so you need to do this in a supercell with sort of image charge correction schemes and so on. And so this is what makes sort of the direct implementation of Koopmans functionals more. That's the computationally expensive part, is computing this guy here. So we would like, in principle, to avoid this sort of explicit charge defect calculations in a supercell. And so this is going to be the subject of Nicola's talk, is that you can reformulate this problem in terms of density functional perturbation theory, and you can do all of this in reciprocal space, so that you can take advantage of all the machinery of Fourier transforms, and this is going to be the subject of Nicola's talk. But note, even for the supercell, we can then perform these supercell calculations only at gamma and then reconstruct a band structure. It's sort of the computational cost of doing this supercell isn't all entirely wasted. Okay, so just to summarize, so when performing a Koopmans calculation, we need to be mindful of these are the different factors that we need to think about, and these are the things that sort of shape the calculation that one has to do. So you need to be aware of the flavor of calculation that you're performing. You need to think about how we're treating the orbital density dependence, and specifically how we're initializing our variational orbitals. And note that this depends on the flavor of the functional that we want to use, and whether or not we're actually going to explicitly minimize the orbital density dependent functional, or we're just going to initialize them using maximally localized value functions and neglect the ODD dependence, and exactly how we calculate the screening parameters, so by finite differences or density functional perturbation theory, or indeed learning using machine learning, which we've managed to do as well, but I'm not going to talk about here. Okay, so these are some results actually that I think I will skip over that Andrea already showed, that we get good results for molecules, and just not only just for the ionization potential, but also for all the orbitals throughout our system, getting nice quantitative agreement with experiment. I think these aren't results that have been shown already, so this is now for solids, now done still in the supercell approach. So here we're just looking at the experimental band gap compared to the theoretical band gap. And we can see that across this set of typical, I think it's 30 semiconductors and insulators, we get a gap that's got a mean absolute error of around 0.2, 0.3 electron volts, which is comparable to the sort of very high quality quasi-particle screen GW with vertex corrections. But also, if you look at the absolute position of our ionization potential, so this is to do with this alignment with the vacuum level, we massively outperform the sort of really state-of-the-art GW. And again, it's not just the sort of the gap that we get right, but it's all the orbitals. So, well, all the bands. So if you look at here, this is a detailed look at the band structure of silicon, but now we're looking at the energy differences between all sorts of different high symmetry points in your band structure. So basically these labels here, they just correspond to particular points on the band structure of silicon, and you can see that we get a mean signed error that's very small, and a mean absolute error of 0.1 electron volts. And then finally, one little project that I did with a Bright Master student is that we actually applied Koopmans calculations to the model system of Hooke's atom. So Hooke's atom is a toy model where you've got two electrons and they're inside a confining harmonic potential. And so what's quite unusual about Hooke's atom is for a 2-electron system is that actually you can solve it analytically. So you can derive the exact solution analytically for the system. And so here I'm looking at the sort of the potential that, well, the potential minus the Hartree term that the HOMO is being is subject to. And so firstly, if we look at the LDA and PBE results are here in the sort of orange and green, and then the exact result is down here in blue. And in this scenario, what the Ki potential does is effectively is a rigid uniform shift of this potential. And so it takes the green curve of the PBE here down to this, well, it's not showing up very well, but it's this lower one here, this, well, it should be purple curve along there. And so just to emphasize, this sort of rigid shift is done without any knowledge of the exact solution. We've only got the physics of the PBE and this sort of condition that we're imposing that we want these sort of orbital energies to correspond to total energy differences. And so this is, you know, this is very nice. And, you know, you might be worried about the fact that we sort of then don't get the long range sort of behavior at large distances exactly right. But if you then look at these sort of, you know, when you multiply the potential by the orbital, like Andrea was doing in his talk, or furthermore, ultimately you've got to then, you know, multiply it by a prefactor of r squared, the results that you get for all of these different Koopmans functionals compare really well against the analytically exact solution. Okay, so there are some important caveats to make. So, you know, we get these fantastic results, but there are some key limitations to this method. The first limitation is that this method is restricted to systems with a non-zero band gap. So it can be very, very small, but we can't apply this method to metals. The reason is that our statement about the sort of the core idea where we want to impose this condition where total energy differences are equal to orbital energies is a statement about the diagonal elements of the Hamiltonian. And so the moment that you have a band gap that is zero, you start to have off-diagonal components in the density matrix. And so we don't know what the appropriate correction would be to those off-diagonal elements. And so for the moment, we're restricted to systems with non-zero band gap until such time as we have a flash of inspiration. But this is not all that bad, because really a lot of the sort of remarkable failures of density functional theory are in systems that sort of dramatically underestimate the band gap. There are two other more technical details that I think I will skip. Well, no, I can mention them briefly. So basically, we have this heuristic approximation where we localize empty states, which is not formally justified by the form of the ODD. And secondly, having an ODD can break the crystal point symmetry. So sometimes you get these solutions that break symmetries. There are tricks that you can play. So there's a publication here by the Guitao Yang and co-workers, but we haven't yet explored these sorts of methods. But perhaps when we come across a really troubling problem, we might do so. Okay, so the general workflow that one has to perform when calculating these Koopmans calculations is you need to define and initialize a set of variational orbitals. You calculate the screening parameters, and then you construct and diagonalize the Hamiltonian. So that's sort of a general workflow, but it can be quite complicated. So here's that workflow as drawn for when we're calculating these total energy differences. So within this supercell method. And so you start off with some sort of initialization. So for a set of molecules, you might do a DFT calculation, and then some sort of Purdue-Zünger trick to give rise to your variational orbitals. For solids, you do a vanarization and then convert this into a supercell calculation. And then you need to do all these different calculations where we're calculating all of these different ingredients here that were the elements that we needed to calculate your screening parameter. And then once you've sort of done this, and you're doing this for all of the orbitals in your system, and then finally you can do a calculation and maybe unfold to a supercell. fold back down to the primitive cell to get the band structure. The DFBT approach is a bit simpler. I mean, don't worry about the precise details. It's sort of trying to give you a general impression of what's involved. You've got a much more linear progression of different calculations. But I mean, in both cases, we've got some quite complicated workflows that one needs to perform. Basically, there's lots of different codes that need to handshake with one another. There's lots of scope for human error if you're going to do this all by hand, and it makes the reproducibility of calculations very difficult. And really, you need to be very, very familiar with the method and with the codes in order to perform these calculations. So we didn't like the fact that this is what we were dealing with, and so we've recently released the Koopmans code. And so the idea is that this should take care of all of the boring sort of practicalities of performing these workflows and allow users to really focus on the science and what's going on. So version 1 was released earlier this year. And so what this package contains, it contains implementations of Koopmans functionals within the Quantum ESPRESSO package, but also Python workflow manager that takes care of all of the workflows that you need to calculate. So it will perform a start to finish Koopmans calculation, as well as various sort of typical tasks that you want to do, like perform a vanarization or calculate a dielectric tensor, for example. This is built on top of the atomic simulation environment as the sort of the engine for the workflow manager, but it's under the hood it calls Quantum ESPRESSO. So basically, it's just, at the end of the day, it's just a very complicated and flexible Python script that can just run all of these consecutive calculations. And so the key here is that it doesn't require expert knowledge. How much more time do I have? Okay, well, I'll take 2. Oh, that is not turning up very well, but the Koopmans package takes a single JSON input file, and then it runs the full workflow from start to finish. So just to try and illustrate, this is the full input file for a calculation of silicon using the finite differences approach for calculating screening parameters. And so here, I mean, you might not be able to make it out, but there's just a couple of keywords that are very reminiscent of what you'll see in Quantum ESPRESSO. And then you give this to Koopmans, it will run the full workflow. So it'll run vanarization, it will run it'll construct the supercell and perform these finite difference calculations, and then it will extract the screening parameters and do the final KI calculation and construct a band structure. So this sort of takes care of everything. And so we'll be working with this during the hands-on. And then finally, because it's all written in Python, actually, you don't even need to deal with an input JSON file. You can just write a Python script that does exactly the same thing. So this is a Python script that is performing exactly the same calculation, but without the input file. So this is equivalent. And so hopefully you'll find it very straightforward to use. Okay, and so it also means that you can do you can do analysis afterwards very straightforwardly, because you get access to this sort of Python workflow object that's got an atoms object that's from ASE that is very easy to manipulate, and then a list of ASE calculators and various other sort of objects that are easy to manipulate and probe and access. And so we'll see examples in the hands-on, but this is sort of just to prime you about how the code works. So just finally to conclude, so we've got these Koopmans functionals, and they're more complicated than a semi-local DFT functional, and this has implications for practically the calculations that one needs to perform. And so we've got this orbital density dependence that we need to care about. We've got these screening parameters that we need to calculate. This is all implemented, however, in Quantum ESPRESSO, and hopefully the complexity of the workflows can be handled by the Koopmans package. And just again, to advertise, like Ismaila mentioned, so we've just recently had this paper come out in JCTC, which describes really everything in detail. So if you're sort of curious about anything, this is probably a good place to start. Of course, of course, we're here to answer questions today and tomorrow. And so finally, I'd like to acknowledge co-workers, or recent co-workers, but also I'd like to thank all the people who have worked historically on this project. And thank you very much for your attention.
Thank you very much. Question. Yeah. Thanks, Leonard. Really nice. First of all, really remarkable results, and it's nice to see that it's kind of mature now, so you would be able to like more users.
Yeah.
Be able to use it. My question is, how robust do you think these protocols are for actually running code, and what would be the challenges of, like burning some node hours and calculating this for thousands of materials and creating the first Koopmans bracket database for
Yeah. So in some senses it is mature, but in others it's not. So when I was sort of writing this the Koopmans package, obviously I sort of felt a little silly doing this, sort of being in the same group as the guys who develop AIDA. And so the Koopmans package is a lot more simple than AIDA. So it doesn't have the sort of things like sort of error recovery, and these sorts of things become really important once you start doing high throughput. It's also not, there are various other sort of bells and whistles. I mean, I call them bells and whistles, but really they're sort of key if you want to perform these calculations in a really high throughput manner. I mean, we're looking into sort of an integration within AIDA, but until that time, I think basically it's better to think about the Koopmans workflow manager really more as like an executable like pw.x. That is ultimately it's just doing a single calculation, but it doesn't really have much more functionality than the pw.x executable has. It will do a series of calculations, but it's not really doing stuff that's more sophisticated than that.
Okay, good. I mean, since that they have latency already done, it would be a matter of like writing native functionality to like writing a plugin.
Yeah, there's a few complexities in terms of the fact that everything that you put inside of it, AIDA needs to conform to certain things. But but then there's all sorts of things that one would really be able to benefit from. For example, the calculation of the screening parameters in principle is embarrassingly parallelizable, because you can calculate for each orbital in your system, you can calculate the screening parameter independently. So we don't currently exploit this. We sort of just perform these calculations serially, but something like AIDA, which can dispatch calculations, that would really help. Although I should specify, just to avoid sort of making this method sound more expensive than it actually is, you don't necessarily need to perform calculate screening parameters for every orbital in your system. You need to perform these calculations for every non-equivalent orbital in your system. Because say you perform a calculation on silicon, all of the value orbitals are identical. And so if you calculate the screening parameter for every single one, you get the same value of alpha. And so you only need to do, in that case, one alpha parameter calculation. But so I'm getting off track, but yeah, to say how I see it.
Could you go back to the slide 6 where you showed this for 1, 2, 3? Would you get the same trend, in particular for the PV delta CF, for solids, for crystals? And then I have a follow-up question on that.
But the same trend, but so we get there. So what was the question?
So do you expect the same trends, meaning at infinity for solids? Delta CF and CPD would be the same.
Yes. Yeah, I mean, just by exactly this logic here, right? This holds for solids.
So following what Andrea said, if I'm taking silicon, and I'm so in that case, if I use the exact DFT, so I don't have to be at the exact the Orbital one would be wrong. But if I do that ICF, the exact DFT of the exact angle.
Yes. Yeah.
Now I'm starting to build a supercell. The supercell is exactly the same. So of course, as I'm increasing the supercell, the exact function result will be flat in the change, right? But in the other case, we have a bigger cell, we got 1 electron, but still it would be exact. So I assume it should be also that, right?
For approximate DFT.
No, for exact.
Oh, for exact DFT.
With the tacit method, as I'm going to infinity with the supervalue, would they match on the limit, or would they stay different?
The augmented FSCM. The augmented FSCM.
Yes.
Yeah.
Maybe that's what.
Yeah.
That's that. So
Yeah.
this means that infinity that's still different. Right?
Yes.
So you don't get this argument.
No.
No. But I mean, this is the idea. So
No, the augment. So yeah, the augment.
Wait. Wait, no, the gap doesn't. No, that they wouldn't converge to the same result for the exact density functional theory. And so basically the idea is that either we can improve our functional or we can sort of apply one of these sort of Koopmans corrections.
You would get the same result. You would convert to the same value. Then we start from different value.
No, they would stay separate. So the exact DFT will get the right result. They'll be different by the factor of the derivative of discontinuity.
So
But you wouldn't have them converging to the same result. Yeah.
Don't
Yeah.
match, and you don't get this relationship.
Yeah.
You do not.
Yeah, because so now for the augment, so the ice of one minor orbital is an exact property of DFT. Because it depends on the exact. So in exact DFT, you get the exact form.
Yeah.
And if you evaluate the augment with the FSCF or so the ionization potential with the FSCF or with minus form with the exact DFT, you get the same result.
Oh, yes, that's true.
Because it's exact DFT. So the augment is correct. It's a different story for the band gap. Because in band gap, so the LUMO from the DFT will mix the derivatives in any case. While if you do a delta CF, so it means n+1 to the n of 1.
Yes.
That would be exact. So the gap would be different, even if in exact DFT.
And it was the range.
Yes, but they all not.
Okay, they're all from the start.
Yes.
Yes.
Okay,
Yeah.
but talking about the gap.
Yeah, this is for the first integration for that. So this was confusing.
Yeah.
This is only for the onward.
Yeah, this is not like yeah.
Yes.
If you want, I can just add that typically with local and semi-local functions, that is the critical condition, you need to have the delta CF worsens going to extended system exactly because of the local and semi-local dependence. If you have the exact potential, the delta CF would stay correct. And so you would keep going with the same difference, connection gap, exact gap, derivative discontinuity. But it's exactly because of the derivative discontinuity would show in the delta CF, keeping it correct. That is exactly what we missed when going to large system.
No, I understand. That's all this argument of the derivative of the correct argument that there. So this you can apply to the wrong solve it.
Exactly.
Yeah.
Can you Koopmans strategy be used for solid with non-linear magnetism and
Soon. Yes. Oh, is it? Sorry? Yeah. Yeah. So there's a collinear, and then there's a Angelo and Nicola have an implementation in for spin-off couplers.
Let's say one slightly cobble on the side and it's valid in DFT with ODJ. Okay, so let's say I apply plus U, I open gaps, and now we can apply Koopmans package. But what would be the motivation to use Koopmans? I mean, should I leave with the DFT plus U solution? Or if I'm not by use Koopmans again, like more correct band gap, more correct dispersion and position of band.
The motivation to use Koopmans really is that the idea of the band gap is much more well-founded in the Koopmans construction. So here we really have meaningful eigenvalues like the DFT plus U. It's this sort of correction to total energies that happens to have the right effect of opening up the band gap, but I don't think there's any fundamental reason why DFT plus U should guarantee that you get good band gaps. Whereas here we're sort of explicitly targeting this property, and so I think you can expect to get a better band gap. The thing that would be interesting, that sort of to disentangle is whether or not there's some sort of non-orthogonality between our different methods for calculating the different parameters. So your U parameter and then your screening parameters. In principle, they sort of derive from different processes in terms of how you calculate them. But there may well be some, well, there will be some interdependence because it affects total energies. But as for the curvature, there might also be some sort of subtle effects that you need to have some sort of, we need to think about exactly how you would sort of disentangle those two sort of recipes. But yes, no, so I think the big difference is really having well-founded sort of band energies that are sort of formally meaningful in the Koopmans framework.
I was Koopmans, or with Koopmans, you can get a quite reasonable band gap, let's say 90% or 80% block with 7. And with Koopmans, I get the remaining 20%. But I think, yeah.
But also, I think you get peace of mind. Like, I think DFT plus you've not, like, there's no reason for it to get good band gaps, fundamentally. Like, it does reasonably well, but like, yeah.
Yeah, I mean, the comment on this, I believe, I mean, the Koopmans is very much, I would say, development on DFT plus U. So there is also the piecewise linearity in Koopmans in DFT plus U that is one of the conditions. So you get closer to the Koopmans condition when you apply DFT plus U. So that's why, you know, I was making this parallel. So,
yeah.
But yeah, the rigorous way of doing it, but maybe more cumbersome would be. I try to speak in an unbiased way here.
Yeah, no.
I recognize the practicality of DFT plus U, and I would say the maybe elegance of Koopmans, especially the way you present it. So yeah, and I had a question in this calculation here. So you're looking really at when you look at the energy of the N-1 system, you really have a charge, localized charge in the system. So you need to apply a periodical mesh correction. Yeah. And there are different ways of doing that. So do you always use the same way, and which way it is, or is there a flexibility in the workflow?
Yeah, there's flexibility, well, there's some flexibility in the workflow, and also some just practicality. So we've got a couple of ones implemented. So there's a Gigi Balderiski and Makov Payne, and then there's a Martina Tuckerman correction as well. But some of these are implemented in the KCP code, which is the sort of one that implements the full minimization, and others are implemented in the KCW code that Nicola will talk about shortly, that does the DFPT. So yeah, so we don't have sort of universal coverage, but we've got some image correction. Yeah.
Just ask a follow-up. Sorry.
Yeah,
it's just a follow-up question on the corrections. Would there be any sort of like added difficulty for calculating materials because the electric function?
Yes.
Do you have already to solve for that?
It's implemented, but we haven't exhaustively tested it. So yes.
Yeah, just a question about the possible application. So I think that in the GW community, one of the big deals at the moment is to treat systems that have a very small gap, because you get these systems with I don't know, tens of few hundred millimeters gap, and then working non-set consistently with GW is a bit of a problem. Then you cannot rely on typical DFT gap. So just wondering whether you would expect any issues in working on solids with very small gap. One is probably spin-off. So often those systems have a gap that are particularly spin-off. So that let's rule it out. So
I don't think that there's any sort of, as long as we can separate these manifolds, which is just the process of bandarization, is just all it needs is something that's infinitesimally small. I don't think there's any inherent reason why we would struggle. No.
And something that comes to mind would be that there was a small gap, and if you not open up the gap significantly, your screening could change significantly. So perhaps your alphas that you computed first may not be.
Yeah, but we
I'm
sort of,
just
well,
thinking loud.
so in principle, yeah, you could do this sort of self-consistent approach and you should be immune to that, but.
So, later, the bank gap, the ground state property. While in the presentation of John Preview, he said it's both ground state and the excited state property. But Koopmans is a spectral function. So we should say that the bank gap is the ground state property. Why we do it spectral function? Why don't we deal with functions that are the ground state instead, like not spectral?
So why does John Purdue say that it's a ground state property or what?
No, Purdue say that the bank gap is the property which is ground state property and at the same time excited state property. I mean, ground state property because it's you can see that the total energy differences like n+1 minus n-1, so total energy is ground state. But on the other hand, it's excited state. I don't remember why. So
Okay.
we need to check the
Well, yes, so in principle, what one could do is instead of bothering with Koopmans, is that you could calculate all of your orbital energies by performing these sorts of total energy difference calculations. But then in the process of sort of like reconstructing your band structure, you'd basically be doing what a Koopmans functional does already. And so yes, so basically we are sort of bridging that gap, right? We're sort of tying everything to total energy differences in our calculations. So we are relying on the accuracy of our base functional for ground state properties. And we're sort of tethering those to the quasi-particles that one ultimately calculates. So in that sense, we need a spectral functional theory in order to sort of bring everything together, but ultimately the physics that's going into it is just that of ground state density functional theory. If that makes sense.
Yeah, the reasoning is pretty much so you can do initial potentials for time getting to couple cluster, and or you can use GW, say, and of course GW is needed for deeper and higher level states, but also needs to get the edges of the correct. So yeah, this dual situation you're mentioning for this, which the reason why you can imagine.
Okay, no more questions. Can I get one again?